Professor Hafner, if you don't remember. Dr. Acosta is traveling, so I'm going to cover today. So let's see what's going on. If it looks hazy in here, it's because I was using party smoke for the demo. Okay, but I won't do it with you in here. I was doing it earlier. So if it looks hazy, it's not your eyes. It is a little hazy. I'm worried it'll set off the smoke thing and whatever. Okay. Number two, we graded the exam yesterday. Everything was almost exactly the same. Average is about the same. Grades are in Canvas. Dr. Acosta will probably post the solution soon. He'll probably put a message about the exam or something. And then I'll give them to the office where did you pick them up at Herman R. Brown or BR or Brockman? Brockman. I'll give them to Brockman so then you can pick them up. So that's all happening. So it was fine. It was a normal exam. Everything went fine. What else is going on? I heard Nod went really well. So on that. I'm usually anxious at parties and want them to end early. So actually, to me, that was an ideal party. You know, let's get out of here. Let's see. I think that's it. Okay, so my job is to start. Oh, I forgot. The other thing is, I hate whiteboards. Okay, for me to write on a whiteboard is like having to have your picture taken with some horrible politician. So don't think about the fact that I'm writing on a whiteboard. They represent like the decay of academia, the capitulation of the corporate mindset, the bullshit thing that we care about environmentalism. Clearly we don't. I hate them, okay? So even though I'm like lecturing, like kind of under control, underneath it's like white hot rage. Okay, the whole 50 fucking minutes after write this thing. I brought all my own supplies. But ask questions. Please, feel free to ask questions. I can control myself pretty well. Okay, I think that's all the intro stuff. Now what we're going to talk about is electromagnetic plane. See, my handwriting already sucks. Interference. There's no friction. It's like trying to write on a seal, like a wet seal, and you're just all over the place. Okay. So you might say we've done interference, we've done waves. Is this plane wave interference, I can't even spell, just this? Is it just, okay, well, let's see. We're going to plot the E field versus X or T, and it's going to be a sinusoid, right? It's a traveling wave. Let's plot another one. Constructive interference. Okay, let's do the other case. Let's plot the E field versus X and T, and say, what if it's like this? Destructive interference. Done. Next, right? So you could just do interference that way, okay? But we do have to do a little bit more, okay? The reason is, really what it comes down to is you don't see the electric field, okay? The electric field is not observable when it comes to light. You only see the irradiance, or the intensity. You're calling it the intensity because you're stuck in the 70s. The proper word is the irradiance, okay? Or intensity is very common. It depends. Some fields use intensity, some irradiance. Optics usually uses irradiance. I think high energy does call it the intensity. But the watts per meter squared is the thing that you actually observe. So we're actually going to do this sort of more mathematically. Let's actually consider two electromagnetic plane waves overlapping. Oh my God, it's so free. I just can't. Overlapping in space, right? So here's some space, here's X and Y, right? And what's happening in this space? Two electromagnetic plane waves. Here's one, K1. That's my symbol for an electromagnetic plane wave. Okay, when you see that, you got to imagine it's like high electric field, low electric field, high electric field, low electric field, in this whole plane moving through space. Right? You know what a plane wave is? It means the E field's constant on a plane. And they're infinite. I'm just showing you a little piece of one. So we've got one here, and we've got one here. K2. And the question is simply what's going to happen mathematically when they overlap. Okay? But let's make the problem a little easier. Let's make some things the same. Let's make the wavelength the same. Probably pretty wise, right? Therefore, K has to be the same. Okay, the wave number is 2 pi over the wavelength, got to be the same. And since the speed of light's constant, the frequency omega must be the same. So we're going to make all those the same, which is nice. We got that going for us. Let's make a few things different. Otherwise, the problem has no meaning. It's literally, yeah. Mm-hmm.
Why is the frequency the same because of the speed of light? Like, is it because we're in the same medium?
Yeah, the same medium.
Okay.
Yeah. So they both have the same omega equals ck, and c is constant. Yeah, this is EM plane waves in vacuum, no materials, all that kind of stuff. We're just doing the very basics. What's different? Let's let them have different amplitudes, which I would call like E naught. Like maybe one is 2 times higher volts per meter than the other. All right, cool. So we're being a little bit general. Let's let them have a different wave vector. And maybe they even have a different phase constant. Maybe they hope we're going to do phi's. The notes I emailed out, if you printed them, are half phi, half epsilon naught. Sorry about that. I was updating it to phi for you people because y'all did it in terms of phi. And I got halfway through and I sent it to you and then I realized I didn't finish. Yes?
So is the k direction vector and the k wave number 2 different values?
That was my next thing, so you get to answer it. So, how can you have the same k but a different k? Why is one the same, one's different? Anyone know?
Is the top one just the amplitude of the
Exactly.
vector?
So one thing if you haven't realized yet, the wave number k, 2 pi over lambda, is the magnitude of the vector that tells you where a wave is going. Okay, so these are actually the same thing. One is the magnitude, one's the direction. So the only difference is the direction of the 2 plane waves. We're not making them go the same way. Excellent. All right. So now let's write the expression for each plane wave. Here we go. E1 equals some amplitude vector, E01 cosine K1 dot R, what? Minus omega t plus some phi, some constant. Oh my God, phi1. Right? And then E2, we're going to talk about all these terms, make sure we're all good with them. Vector cosine K2 dot R minus omega t plus phi 2. Right? So there's your 2 E fields. One is this one is this one. The only thing that I think looks weird to you is K dot R. That's just a way of doing a wave that's going anywhere. Right? Most usually you see KZ or KX, that means the wave's going along X, the wave's going along Z. Here, this is just a way to write it. It's just anywhere. It's not specific to any specific direction. If you think about what K dot R is, it's Kx times X plus Ky times Y plus Kz times Z. Right? So that's just a more general way to write that. All right. Now, next question, for those of you who are really into the math. Those plane waves are solutions to a differential wave equation, which is linear. Therefore, all solutions obey the principle of superposition. All right, so if 2 overlap, E sum is E1 plus E2. If you didn't know the answer to what I was just saying, don't worry, I didn't know until I was about 43. Okay, and I taught this class for the first time. It's like, oh, that's what that means. Okay. So we're done. E1 is just, that's all you gotta do. You just add them together. Right, so for getting the total, you literally just write this plus this and you're done. There's really not much else you can do. But we don't observe the electric field, we observe the intensity. So we want to know what is this thing y'all talked about, the intensity of the sum, which is the time average of the magnitude of the Poynting vector, which is, I'm going to write it epsilon naught c E sum squared. Okay? So I think you usually see this 1 over mu naught c or something. So why would we put a 1 over when we don't have to? That's the beauty of c, mu naught, and epsilon naught. You can write it however you want, and you have to, your equations are like shorter if you don't put in 1 overs when you don't have to. It's just life advice. I mean, you do what you want, okay? So now, one thing we're going to do here, so this, the way I'm going to describe plane wave interference is going to be a little more general than Dr. Acosta's notes. So he does it in 1D. Okay, so 2 waves going in one axis, and they're offset by a little bit. So if you look at his notes in that derivation, it'll look a little different. It'll get the same answer. Here, we'll let him go in 2 directions, arbitrary directions, and we'll see how far off they end up. But I want to point out that there's still lots of secret little approximations I'm making here that I'm not going to tell you. And you can see if you notice them, it'll be fun, right? And then you can ask me, okay? There's lots of little things we're going to do. And the point is, what I want to let you know is we can't really do everything, okay? There's little things that, maybe you've already noticed I've glossed over things. Like, I'm just going to write this and call it E squared and not even really worry about it. Okay, it's really magnitude squared, it's really E dot E. We don't have time to explain all that, okay? So just call it E squared and go with it. The main thing to look for is that there is a difference between the amplitude, that's a constant, and this varies in time, right? So E1 is the whole thing varying in time. E01 is just that constant vector. So just to let you know, there's various levels of reality here. So we're going a little closer, but not too wild. And at the end, I'll show you, like Acosta's from his notes and from these notes, and it's really the same thing. All right, here we go. Where do we go now? I guess we're over here. I'm going to write on myself. I'm going to lick something, and it's going to go everywhere. I sum then. Okay, so what is I sum equal to? Well, it's literally just, we just put, let's pull out the epsilon naught c and write these big brackets, and it's just e sum squared, right? So, well, it's just e1 squared plus e2 squared plus, oh, there's a cross term. Do they still call it FOIL? E1, E2. They still call it FOIL. Good. Thank you for telling me. And this is where I'm getting sloppy, obviously. I'm like, E1 squared, E2 squared. Don't worry. It's dotted with itself and the square root, who knows? E1 squared, E2 squared. Let's get on with our lives. Okay. Okay, so then what is that? Well, then you could say, oh, people on the bottom can't see. Let's see, I sum equals, I'm used to like a stage, swooping. I mean, this is. So remember, you can break things out of these brackets, right? So epsilon naught c times e1 squared, that's just the original intensity of the first plane wave. And that one is just the original intensity of the second plane wave. And this is where the magic happens, as they say, right? That's the extra term. That is epsilon naught c times the time average of, well, we can pull the, well, the 2 can go, it doesn't matter. E1, E2 of those two. Without the knots, that's still the full thing, okay? So this is called the interference term in optics parlance. And it's usually written I12. It's like the interaction of the two waves, okay? Cool. So now we've gotten it down to something that is kind of exciting. We've got to figure out this. Mathematically, what is that? That's where the action happens. Okay, do erasers work? Yeah, you know. It's not bad. By the end of the lecture, I'm going to be like, I love whiteboards. This is the greatest thing. I take it all back. Throw these markers in the trash. Kill some dolphins or whatever. What was it? I've heard somebody say, now that we can't have plastic drinking straws, I'm just choking turtles with my bare hands. Okay, so let's plug in E1 and E2. I stole that, okay. From a great physics grad student person who's very funny, and named Tanya Sabrina. On Swiffer. E1 and E2. So we're going to plug those two things into there. Okay, now things are going to get ugly. Okay, are you ready? Here we go. We're going to plug in literally that big massive thing in like this. I'm going to skip a line. And what's going to happen is we're going to go ahead and pull out the 2 epsilon naught c. That's already out. It's the plug in there that we're doing. But we can take constants out, right? So we might as well take the amplitudes out. The E01, E02, right? So let's go ahead and write all this down. There's some constants, right? Those don't care about the time average. And let's go ahead and take these out just to save writing. I can only write so much in 50 minutes, right? And now what's left that has to go in the time brackets are the 2 cosine parts. Cosine, that was K1 dot R. I'm going to put the phase first. Ooh, minus omega t. Why is he putting the phase first? There must be some magic reason. K2 dot R plus, ooh, the phase first again. Oh my God, you're so easily amused. Jesus. Okay, so when you have a time average and you're trying to simplify it and it's got some omega t's in it, you want to isolate the omega t's, right? We can't take the time average of this. But if that omega t were by itself, then we can take the time average of it, right? So what we want to do is isolate omega t with the sum to product rule regarding sines and cosines, all right? So there's some general form of it where it's sine minus plus cosine plus minus, I don't know. I'm just going to use the one that works here. We'll look it up. That's why we have the internet. I didn't used to have the internet. So you have the internet, so there's no sympathy really. So what we're going to do, but now the tricky part is how do you use it? I mean, it looks like we want to do the product to sum rule. No, we're actually going to do the sum to product twice, right? So we're going to call this alpha right there, and that's going to remain omega t. And we're going to call this beta right there, and that's going to remain omega t. Okay? So let's apply the sum I12 to epsilon naught c, e naught 1, e naught 2. Still the time average. And let's see, when you have the a minus cosine x minus y is cosine x cosine y plus sine x sine y. We're really going to write that down. Cosine alpha cosine omega t plus sine alpha sine omega t. That is just the first term. Then we're going to do it again with beta. We really are cosine beta cosine omega t plus sine beta sine. See, if you don't do the, oh, can you write on wood? Can you write on the metal?
One way to find out.
Okay, good. You got that. I don't want to get fired. See, it's just pathetic. Okay, so now it looks like I've made things worse. You're like, what do you do now? I mean, these things are here, and we can't apply the thing because they have to be multiplied. We have to FOIL this. Surely we're not going to FOIL that. Oh, we are going to FOIL it. I mean, come on. You'll never do this in your life. If I don't make you do it right now, you'll go on and you'll just never have experienced the magic, okay? So first terms, what do they look like? It looks like cosine alpha, cosine beta, cosine squared omega t. Cosine squared alpha. I'm trying to write better. That's why I always say everything I write, because I know you can't read it, okay? So the first gave you a cosine squared omega t. Let's do the outer. We're literally doing FOIL. We did first, now we're doing outer. Awesome. Let's do the outer. No shit. No, we're doing last. We're doing FLIO. Yeah, we're doing last. Sine alpha. Shit, now I've screwed around. I've lost track of what I'm doing. Sine alpha, sine beta. Cosine. Yeah, sine alpha, sine beta, sine squared omega t. That's nice. Now, what about the cross terms? All right, so first and last, so we've got first times last, you got a cosine sine, and middles, you got inners, you got a cosine sine, and then the thing in parentheses, I'm finally going to throw in the towel. I'm going to say terms. Okay, so the thing in front of cosine sine to be just the long thing that I've run out of room to write. Okay, you'll see why doesn't it matter. Does anybody want to shout out and ruin my flow of why it doesn't matter? Go for it. Why do I not care about those terms? Let's do our time average. Somebody shout it out. Somebody have it? That's right. The time average will be 0. This is a half. Cosine squared, sine squared. You know those are a half. You've been told those are a half. You've never been told that's 0 because we don't usually show you this stuff. Okay, this is like now. Yeah, the time average, sine squared, sine cosine will just go up and down symmetrically, so the average would be 0. So that makes this big, ugly, long term go away. All right. So now we actually got rid of the time. See, this is a half, and like we got it to where every term was just multiplied by something that was just omega t. So we're able to take the time crap out of it. But we're still left with cosine alpha, cosine beta, plus sine alpha, sine beta. What are we going to do with that? That sounds like a disaster, doesn't it? I feel like there was something just 4 minutes ago. What is that equal to? Cosine alpha, cosine beta, plus sine alpha, sine beta.
Oh, that's cosine of alpha minus
It just
beta.
hit you. Isn't that beautiful? Isn't it exciting when it hits you? See, E naught 1, E naught 2. It's just the product of some rules, some backwards, right? It's just cosine alpha minus beta, right? There it is. That's the 1, 2 term. And alpha and beta are just these things, right? Isn't that amazing? And you might say, oh, it still has time in it. No, it doesn't. Alpha and beta don't have time in it. We have taken the time out of it, okay? So like if you're trying to do something like this on your homework and it starts blowing up like this, you've usually made a mistake. Okay, but if you're doing it just right, suddenly it comes back together. If you're being shown how to do something that somebody figured out 400 years ago how to do. It may not always work out if you make any teeny error or you're trying to do a problem that's intractable, which most of them are. Okay. See, when it hit you, that's when it hit me. That's where I went, oh my God. See, I was supposed to shout out, oh my God. Sorry, I missed that one. Okay. So now what we can do is, let's clean up a little bit, and we're going to write that out and rearrange it a little bit. This is a 75-minute class, right? I know. And thanks to the person who told me that class was at 10, because I thought it was at 9. So. Okay, so what we want to now do is keep messing with this cross term, this I12. Let's see where we are with it. I12, the interference term, epsilon naught C. It's got a 2 going on there. It's got the 2 amplitudes. E naught 2. And now we have the cosine. Now we want to put in alpha minus beta because that's really where all the physics is, alpha and beta, right? That has the KRs and the phi's. But we want to group them. If you'll permit me to save time so we can do more fun stuff, is I'm going to go ahead and group them, right? So it's really this minus this, okay? But we want to get the K's together because they cause one kind of an interference effect, and we want to get the phi's together. We don't want to just write this minus this. We want to say K1 minus K2 dotted with R. Right? So this side is minus just because that's in the sum to product rule, right? So that's A minus B. So that's why it's K minus K dot R. And let's do the phases, well, that's all that's left, plus phi 1 minus phi 2. I meant to write bigger, but there's nobody sitting in the back, so I guess it's okay. Is that right? Well, it looks too simple. No, that's right. Yeah. Okay, so this thing is very important. This is the phase difference. All right, so that tells you how the two waves are going to interfere. Oh, sorry.
For the old wave, there's like a 1 half and then a 2. Was the 2 supposed to cancel with the 1?
Oh, yeah, let's see. Oh, probably. Let's see. Why do I, oh, I don't have a 2 here. Yep, let's see. So the 2 canceled here. So what's really scary about lecturing is you're halfway reading it off notes and you're halfway doing it as you go, which often leads to little collisions. So I love it when people are nice and let me know. Now they say, you're 2! Where'd that half come from? That's how they usually would act. In the 2000s, you guys are much more chilled out than that. Let's see. Yeah, so yeah, the 2 got rid of the 2, so there's no 2 there. So now what we can do, though, is, so this is our phase difference. This is where all the physics is going to happen. But let's really, just to have a victorious moment, let's write the full I sum, okay? It was the intensity of the first wave plus the intensity of the second wave plus this thing, epsilon naught c, the 2 electric field amplitudes. You want to cosine of this thing. This phase difference is called delta. Okay, a phase difference, comma, delta. Where delta equals this thing, K, just summarizing here, the difference in K's dot R plus the difference in phases, the phi's. I'm really bad at Greek letters, especially for someone named Jason, but you'd think I could do them better. Okay, so what is the result then? So it's, the result is a constant intensity modulated by a sinusoidal interference term. There's way too many E's in that. So as you can see here, the constant intensity is from the 2 things, and it's modulated by that. That's all that's happening. And all that is the first things that, oh, when they're constructive and destructive. Now you know a little bit what happens in between, right? And what you'll see is 2 things can contribute to the phase being different. So when you do different kinds of problems, there will be times when this contributes, and there will be times when this contributes. So we're going to go over that. We're going to start talking about that when we get to Young's double slit. We're only halfway. Okay, class is half over. I screwed around for 5 minutes, so we're in pretty good shape. Okay, cool. So now we're going to look at my visualization of 2 plane waves overlapping. Oh, I also have to tell my joke. Hold on. No, it's more of a Young's double slit joke. No, it's more of a diffraction. I'll tell it anyway. Okay, so what this is this is going to be just this was how we did graphics when I taught this class. It's all PowerPoint. Okay, so here we go. This is a plane wave. Okay, thank you. So loud. And red is like up in the electric field, blue is down, and they're transparent. So when they overlap, where they could destructively interfere, they're purple. Right? The high red over the low blue is purple. And when they constructively interfere, they're even brighter red and blue. Okay? So we're just going to let them fly across, just like in the initial diagram. And you see, here they go. They're starting to overlap. And there you see bands of purple. Look at that. And the bands of purple don't move. which they shouldn't, right? Because our answer just said there's these constant bands of purple that only depend, it looks even better from here, you should lecture sometime, that only depend on space, they don't depend on time, all right? So let's watch it again. Oh, I did that. So while your parents, you thought they were watching you play when you were 5, this is what they were doing. Making stuff like this. Right, so there it is. So the bands don't move, and they're sinusoidal in space and all that stuff. So it's just like what we saw. Okay? So let's see. I gotta keep my advertisements. Because if we don't get enough people in this class, they'll make me teach 126 again, and I'll have a nervous breakdown. People have to sign up for this class. It's like medically important to me. I can't afford all that therapy again. Okay, so now let's talk a little about the physics of the phase difference. The physics of the phase difference. Delta. Okay? So I think I have some notes that kind of help you think about that. Let's see. So we already wrote it here. I won't write it again. Delta is that. Let's see. The K dot R's, what does K dot R do? They count waves in space. Okay, so if you keep going on like optics and waves, eventually you have to accept what K is. Okay, you're probably starting to accept omega, and you're kind of okay with radians per second at this point. But K is even better. K is literally, it's a spatial frequency. Like omega is how many radians of wave per second. K is literally how many radians of wave per meter. It's just a spatial frequency is all it is. It's just our brain does lambda because we think in terms of wavelengths. But you can also think in terms of spatial frequencies. That's what K is. So if you multiply your number of waves per meter times how far you go, you're just counting waves. Okay? Just like in frequency, in time you're counting waves. K just means in space you're counting waves. So if your two things go slightly, if your two things you're interfering started together and they go different distances to get somewhere, this will give you the interference effect due to that. So it covers the case where waves go different distance. I write meter on chalkboard. Okay. So that's what these terms do. You can see it's the difference in how far they go, basically. K1 daughter, K2 daughter. And then the phases, phis, really technically it defines the origin. Is one thing it does. You know, like, are we doing this with a sine or a cosine? Where's 0, whatever, right? So you can definitely at least set one of them equal to 0 to start. They don't both have to be a value. But what they do in physics is it covers phase flips, okay? Phase flips. So phase flips, meaning when a string wave hit a heavy rod and bounced off, it inverted, right? At a phase shift of pi or 1e. So when light bounces off glass, it also has a pi phase shift, same thing. So when you're doing optics, so when you're doing Young's double slit like we're going to do today, there are no pi's because the light doesn't bounce off anything. It just goes straight from the slits. When you start doing thin films, then you got to keep up with which ones reflected off of the surface. Because those will, in addition to the difference in distance they went, they'll have a phase shift in there somewhere. So now, this isn't in Dr. Costa's notes, but in optics, like in an optics textbook, you might see this, or you go Googling for things, delta path plus delta, I can't see, I think it says phase. I didn't know that people don't lecture without glasses. They're not over lambda naught times 2 pi. So this form isn't really necessary. You now already know everything. But it's written that way a lot in optics, like when you're doing optics problems. And these are literally distances. The delta path means the two rays or the two plane waves went a certain distance to get there. What's the difference in the distance they went? And you can see how for interference that makes sense. Yeah, if the distance over lambda is fractions of a wavelength, then multiply that 2 pi to get radians. That's all that's happening. But then you can also keep up with the phase flips. Maybe you add a pi here, or don't add a pi here. Or no, well, you got to turn the phase flips into an effective distance, right? So something goes through a pi phase shift, you put a half wavelength there. Then the lambdas would cancel at a half times 2 pi would be pi. So this is just a way to keep up with them spatially. These deltas are both space. Okay? So you'll see that if you start reading a bunch of optics textbooks, which I recommend. Okay. So now, when is it constructive and when is it destructive? This is finally the final, the end here. This is it for the EM part. Then we'll do Young's double slit. Okay. When is it constructive? When is it destructive? So this part you've thought about for other kinds of ways, but let's go ahead and write it all down anyway. Okay, I'm on my original marker and I brought 12, so I am impressed that markers last longer than I remember. Destructive. Okay. Yeah, so it'll be constructive, of course, whenever this total phase is 2 pi times m, where m is all the integers, and it'll be destructive when it's, you can do this 2m plus 1 times pi. Right, so m equals 0, 1, 2, da, da, da. So similar to what you wrote before, when you were doing string waves or whatever, sound waves, all this stuff. Same idea. Constructive, destructive, just depends on if it's 2 pi's or every third pi. So then what you would say for this is you could actually plug this into here, and you can kind of get rid of the 2 pi's if you want, and you can write it more simply. Well, that's if you're doing this method, which you probably aren't, but if you want to do it in terms of phase, you use this method. If you want to do it, some people like to think of everything as a distance. Right? The difference in distance they traveled, every pi flip is a half wavelength, whatever. So then you could write delta path plus delta phase, pH, I wrote R because it means reflections, equals lambda naught times m. So this is a similar thing. It's just saying what is the difference in the two waves when they added together, how many wavelengths, if it's an even number of wavelengths, then it's constructive. And if it's not, m plus 1/2 times the lambda, yeah, that was right, then it's destructive. Delta P plus delta pH, path and phase. Okay? These are all saying just the same thing. You can go plug them in and check. So you can do it in terms of phase, you can think in terms of distance, and these are all for all the m's. -10, -4, 3, whatever you want, all the integers. So now just to help you, if you're reading Dr. Krause's notes later, I'm going to compare. We can look at if we got the same thing or not. And he has in his notes delta x equals m lambda. Right? So that's basically this. His delta x is what I'm calling the path difference. So he did the one-dimensional interference case where it's just two plane waves along x offset by delta x. So that's essentially for us the same as we just did it sort of in 3D. So he got the same thing. Delta x is m lambda. They didn't do anything with phase shifts. And then here he got delta x is m plus 1/2 lambda. Plus 1/2. Right, that's the same thing. M plus 1/2 lambda. So they are consistent. They're just derived different ways and for different levels of generality. Okay. So that is the interference of electromagnetic plane waves. That's it. Okay. So in our remaining 17 minutes, we'll apply it. Another question, a big picture questions about that. We have 17 minutes to do Young's double slit, which is doable. Okay, cool. All right, let's move on to Young's double slit. I'll tell the history of Young's double slit while I erase. How about that? There was this guy. Okay. Not Young. There was a guy named Haughens, Christian Haughens. And he was one of these famous people that figured out a bunch of stuff. Basically, if you were like, really rich and you could just sit around and think all day and you were smart, you got to come up with a lot of physics. Right? So Christian Haughens was thinking about how does light propagate? And this is way back. They didn't even know what the electromagnetic field was. I'm not sure that he knew it was a wave. Just how does light propagate? And he had this, I think drugs were involved, okay, because this sounds really bizarre. And I've seen lots of pictures of Haughens, and he was a party guy and good looking and everything. So I'm pretty sure drugs were involved in this derivation. Because he's like, how does light, I don't know, like, you have a source and light comes out like this. Or sometimes it's like going like this. It was all geometry back then, right? It's like, I don't know, 1600s or something, I don't know. You're like, dude, what if every point in space, the wavefront breaks up into little point sources, and those go out? Whoa. So then he got really deluded, and he just like drew a bunch of curves and realized, oh my God, it's the same thing. That is Haughens' principle, okay? That's my somewhat accurate reenactment of how I'd like to do a full dramatic reenactment with costumes and everything, but we don't have time. Okay? And it works. Okay. So if you, and then Fresnel came in and put in interference. If you do that plus interference, you get this frighteningly accurate description of how light propagates, because it's actually deeply connected to what's really happening, which is completely different from bullshit I'm telling you. It's all photons, really, but it's deeply connected kind of in a way to how photons actually work, so that's why it works. And we're going to use it, okay? So I'm making fun of it. Oh, that's how we do Young's double slit. Okay, so that was Halpin's, and then Young did this experiment where he took some light, right? Plane wave coming along, and he put it through a slit, and then he put it through 2 more slits. So it's the greatest misnomer in the history of physics. Young's double slit requires 3 slits, okay? It did back then. Now we have a laser, so it doesn't require 3 slits anymore, okay? And the reason he did this is you say, well, here, the Stoner Halpin said that we can think of this as a point of light there, and it will start to do this. And what this is accomplishing for us in like the 18th or 19th century or something is a way to get the light from here and here to have the same phase. Okay, so we need light, I don't have time to get into it, but light needs to be coherent to have the constant phase over a long distance. You know, these ideal plane waves we're writing don't exist, right? Those are coherent forever. Nothing is coherent forever. And they were doing it with like sunlight, very not coherent at all. So putting a point source here, letting it expand, and then it hits this one, and that's 2 point sources here. Now those 2 are coherent. So that's all this one is doing for you. These days we have a laser that's coherent, and we put the beam on both of them, and we don't have to have the 3rd slit. That's why you always see it drawn with 2 slits. Okay? So he took that and he cast it on a screen and said, oh my God. It's like, that's what screens look like back. Oh my God. Hold on. Okay, here we go. Well, here, fuck it. There's a screen right there. And he said, what's the pattern of light going to be on this screen? Right? So let's draw the intensity on the screen. And basically what he found is it oscillates. You would think, oh, these 2 things just overlap. It's like 2 flashlights, and you just get a big blob, and you get very strong oscillations. So this was like the first really strong evidence that light is a wave, because it can interfere. Okay? So let's look at it, how we would describe it mathematically. Let's just ruin the beauty and wonder of it and describe it mathematically. Okay? So what we're going to do is imagine a point on the screen. I'll redeem myself with these lines here. Like that. Oh, the marker screwed me. Okay. Dolphin death. There we go. Oh no, I was going too fast for the marker. I can't be constrained by modern markers technologies. Whatever. Okay, so we're going to figure out the intensity here. Right? So here we have 2 plane waves, just like we showed you before. 2 plane waves overlapping. How do they add right there? So we got to think about our, the notes are over. Let's just think about our, no, they're not, our phase terms here. Delta path plus delta phase over the wavelength. If we want it to be, well, this is just what delta is, times 2 pi. Right? Okay. So which one is different for these 2 waves? Somebody shout it out. See if you're following what my deltas are. The path, right? The path is clearly different. One went farther than the other. The whole point of this was to get them in phase, so their phases are the same, right? So the delta phase is nothing. We have to just treat this geometry and figure out what is the difference in path, okay? And now more approximations are coming where I'm going to tell you some of them and you're not going to notice the other ones, okay? So we have some knowledge of this system. We know the separation of the slits is A, okay? And we need the geometry to tell us what's the difference in the path. What you can do is you can define kind of an average angle of how high you are on that screen. You can pretend all 3 are at the same angle. They're obviously not. But typically we're doing this where that angle is so small, they're essentially the same angle. And then you can draw a line like this and draw a right triangle right there. And then that angle is basically that angle, okay? And then this is the path difference. And those 2 are the same. Are they really the same? No, they're not the same. The line you would draw to make those 2 the same does not come in at 90 degrees, but I need it to come in at 90 degrees, okay? So whatever. Okay. So this basically only works when things are really far away. Just some examples of kind of the little BS that's snuck in when you're not looking, okay? So if we take this triangle, this is A, this is theta, so it's A sine theta is the path difference. So we have that the phase is A, the phase factor that we use for interference is a sine theta over lambda equals 2 pi. When is that going to be constructive? Oh, I deleted it. I erased it. Also known as erasing it.
2 pi n?
2 pi m, exactly, equals 2 pi m. M is integers. 0, 1, 2, da da da, like that, right? So you look at it and you say, it's going to be something like as this gets bigger, sine theta gets bigger. So you're going to have your maxima. This is for maxima. When, what do we got here? Sine theta equals m lambda over a. Okay, is where your things are going to show up. So what you're going to get is this pattern that looks like this. Like this, and this one, and this one is m equals 0. Right? M equals 0, the maximum, I'll put max right there, is at the angle of 0. That works out. There's one there. This is the next interesting one. This is m equals 1. So where does that happen? If you want the angle, that happens at the angle lambda over a. Lambda is usually really short. Nanometer scale, a is usually millimeter scale, so it's a really small number. Okay? And since it's small, let's see, lambda is much smaller than a, theta is very small. So you could also say theta equals m lambda over a. Does that still bother you when we say that sine theta equals theta? Because I have a remedy for you. Plot sine theta. Sine theta versus theta. And when you zoom in, what does this look like? It's like a line, right? And what's the slope of that line? 1. So sine theta is theta. When you're near the origin, sine theta is just y equals x. Okay? So sine theta is theta, so there is where your maxima are. So you just have to go up by an angle, lambda over a. But we can even be more annoying. And we can say, well, let's not even call it theta. Because the angles are so small, we can say, y over s, right? But theta basically equals y over s. What is s? S is the distance all the way to there, right? In this triangle, theta is opposite over a j. Well, theta is tangent. You get the idea. Okay. So if you want to describe it in terms of angle, you can do this, but the more normal thing is to describe it in terms of where the maxima are in terms of height. And I've completely lost control of myself here. These notes make no more sense. And it's going to be y maxes is m lambda s over a. We just flipped it around. That's where the y maxes are going to be. So this is typically the thing we use, right? So 0, there's a peak in the middle. The first one comes up at lambda s over a height. So this is now a height, right? This is meters, meters, and meters. So this thing is literally a height on the y-axis where it's going to show up. And you can also get the minima. We'll put that on the homework or something like that. You can get the minima as well, okay? Oh, we have 7 minutes just to enjoy this result with a demo. Do we want to see it in the real world? Of course we do. 7 minutes is a lot of time. Like that, I sort of just crammed it all down at the last minute. So let me know if you have a question. Yes?
What's S again?
Yeah, S is this distance from the slits to the screen.
Okay.
So the reason that's equal is this. Here's your little triangle. It's like S up Y and all the way back.
Okay.
So that's why theta is just that. Okay, so let's see. Need to bring the screen down. That's not the screen. Okay. This is the screen. Down. And then I'm going to turn the laser on. So the laser's in the back. It is 30 milliwatts, which is like 15 laser pointers. So don't stand up and look back here. Okay. So usually this demo leads to a standing ovation, but I'm just asking you, please don't. Okay. Remain seated no matter how amazing it is. So that's the laser with nothing blocking it. So that's like a teeny piece of the plane wave hitting the screen. Okay. So what I'm going to do now is I'm going to put just a double slit pattern on top of it. And you can see it's spread out into something that looks like cosine squared. Right? It's going from 0 to maximum, 0 to maximum, 0 to maximum. It's horizontal instead of vertical. Wow, okay. Not quite a standing ovation. Now we're going to get a case. So let's think about how close the slits are. Here they're far apart. And now here's another one where they're closer together and it spreads out more. So if you think about those y max position, they were 1 over the spacing. Hopefully A was in the denominator. Okay? Because now as A gets smaller, the spacing gets bigger. So there is close together slits, there's far apart slits. Right? And then here, oh, this wheel has all kinds of things. I don't know what that is. This thing is exciting. Let's see. Yeah, that's not so good. Oh, here's multi-slit diffraction. Hopefully you won't have to do that. Another thing you can do is you can see it in space and believe that it really is 2 plane waves. And that's what I was doing with the party smoke. Okay? He died. Okay. Is when you look at it like this with the party smoke, it's like you see these bands that are really amazing. But I'd have to like fog the whole room. And I could do that in HRCNet, but here I'm more. So instead I have a picture of it for you here. So this is what it looks like. That's the spacing changing. Whoa, the bands get farther and closer apart. It's amazing. Look at that. That's like essentially the A changing. Yeah. And then this is the wavelength changing. Oh my God. So it depends on wavelength, just like the equation predicts it depends on wavelength. And then if you look at it, it looks like that with the party smoke. Right? So you can actually see the bands. This is like the plus, the cosine square coming at you. It's bright, dark, bright. At a lower frequency because of diffraction, which you'll learn about later. It's only 10, oops, I messed up. It's 10:46. Somebody ask a 4-minute question. Or I can do the most popular thing and just say we're done. So I need a lot of time to clean up, so I don't say we're done. If you have questions, come ask questions.